So this is one of those combination theorems that we want to add where when we're just inspecting these types of space groups, we can spot when we, by observation, more or less add another um, a set of planes somewhere, kind of like how we derived the one where we had mirror planes with a glide plane in between them in general. And this is actually going to be very similar to that, except that it's going to focus on looking at um, a rotation combined with an offset mirror plane and seeing what kind of perpendicular planes we have from that interaction. And it'll be quite useful for the final set of space groups that we need to put together. 180-degree rotation. And we'll draw some lines in here to guide the eye. Now remember that these lines are actually meant to guide the eye. I'm not changing color, which means they're not meant to be a symmetry element necessarily. So now let's take our true symmetry element that we want to combine with that, which is our mirror plane, the operation represented by sigma. And let's ask what's the equivalent operation. So let's look at a motif element. Let's use green this time as a symmetry element. So I'm going to start here and say, let's imagine we have some element like this, and that element is located a distance x from this black horizontal line, which passes through the center of the rotation. And it is located y distance from the y-axis, which is passing through the center of the rotation. So if we rotate that motif around, of course, we would be at x above here. And remember what a rotation is we flip x, and then we also move over here to some distance y. And there's the rotated about a pi. So again, thinking about from an operation point of view, we've just done a pi, and now we are going to reflect around m. And so when we do that, we have this distance here. And that distance is the reflection distance. And we get the mirror image. So we have 1 here, 2 here, and if we call these right hand or whatever you want to call it, this is still right hand because rotation preserves it, and this is left hand, right? So now let's finish doing some algebra and geometry. So this distance, because the offset distance, we're going to call delta. So this is a reflecting plane or line in 2D that is distance delta from the rotation axis. Well, that's easy because if this is y, this distance is delta minus y, which means that this is also, because of reflection, delta minus y. Now 1 and 3, so 1 and 3 are related by a glide operation because they're the opposite handedness and they're off in the top direction, right? So if we look at this, we can say, aha, 1 and 3 are the same distance x from the y-axis, but they're translated in y. So right away, a simplified way of picturing this would be to say, aha, okay, fine. I actually could do a reflection about here because x is the same. Right? So I flip around this axis here and then I translate. And if I were to do that, this would suggest that there's a glide plane right here that can describe essentially where another plane is for some offsetted delta of a mirror plane. So I'll review this in a second, but so that would bring us over here, and all I have to do figure out is the tau, because for this operation, tau would be this distance, because I would be starting here, and the glide direction here, remember, it just reflects about it, so that's guaranteed because it's x and x. And then I translate tau, and tau is equal to, if you look here, it's y plus delta minus y, delta minus y. So it's y plus delta minus y plus delta minus y. So with that, let's clean up a little bit here because I'm a little worried about our resolution, and so let me just draw the main features of what we're talking about. There's a rotation of a pi, and as I imagine there's some line passing through this point, what I'm saying is that we had started with a mirror plane that was offset by some delta, and we induced a perpendicular glide plane, which ended up having the equivalent tau of 2 delta, right? And so now if I were to write this as a combination theorem, I would say I have a mirror plane, a mirror operation, which is operating on a rotation operator of pi, a new glide plane, which is defined by, we got to put in deltas and things like that. So here we say that this is offset by delta, and then the angle between these guys is 90 degrees. And there we have a nice little combination theorem that should help us. So anytime we see a mirror plane offset from a pi, it means that there has to be a glide plane perpendicular to it passing through that point A, as shown here, and going to be simply 2 delta is the translation. So now that we've derived that for the case of a mirror plane being offset, let's make it completely generic. And let's look at the case for having a glide plane that is offset. So let's start with the same kind of derivation. Remember, these black lines just represent the reference axes for what we're doing. We'll still talk about an A pi, because it's a low symmetry element that can be found in many of the high symmetry things, you know, 6-fold, 4-fold, you know, whatever. So it's a very common thing to have a plane offset from one of these elements, an A pi element buried either by itself or buried in another high symmetry element. So rotation. So now we'll make a this time we'll have a glide plane that's offset by delta off of this main plane. Now let's look at our motif again. Let's draw our motif here and here, and recall let's keep it red actually, just as a change. These are just reference lines, not glide planes. But I'm showing you where the coordinate system, just like on the other one, was. So this would be x and x, and this would be y and y. Now, what happens here is that this element gets moved over here, and then with the glide plane gets reflected over here, and then translated by tau to here. Okay, now what we're going to look at here is the equivalent operation. And you can see here that if I were to somehow reflect this down, translate a single glide plane that would be representing this direction would work. Now it would have to bisect the distance between number 1 here, and I guess we'd call this, you know, let's call it final, depending on how you count, whether the glide plane is a two-step or one-step operation. But you know, it's an implied two, but you know what I mean. So let's just call it the final version. So we rotate, we apply the glide thing, and we end up here. Relationship between this one and this one. If I make this bisecting this distance so that this and this are equal, then I can think of this as a new sigma glide plane. The question is, how far does it move? So the only thing left is, first of all, to identify, you know, how far below this glide plane is. So in other words, I've got one plane here, glide plane offset by delta, right? I get another one, and the thing I want to know is how much is it offset, because clearly it's perpendicular, and if I just say it's, you know, this amount below and perpendicular, that defines the plane. And the other thing I've got to do is define this distance. And I think you could tell this one's the same one as we did before, y plus y. And remember that this distance here is delta minus y. And so because of the reflection part of the glide operation, it's y plus y, delta minus y, delta minus y. So that actually means this one's settled. This is 2 delta, right? And then we just have to figure out this one. So this one might be a little bit trickier. Let's switch to a different color. Let's go back to our green. And let's start to label some of these things. Remember, this is x, right? And by definition, this red one is tau, right? So this distance that gets bisected is tau minus x. So this distance is tau minus x over 2. Hopefully you can see that. So therefore now we have actually what we need. Oh, I'm sorry, I forgot this x here. So this is the full distance all the way down here includes this other x. So this distance here is tau minus 2x, and that would put this here like that. So it's tau minus 2x over 2 is that distance. So now I can see that, aha, what is this? This is tau minus 2x over 2 plus x, which I think you can see equals tau over 2. So now we have our theorem, our combination theorem for an offsetted glide plane, and it is, let me use the similar colors like I did before, sigma tau, right, whatever that translation is, which is operated on after a rotation, results in a new glide plane that's 2 delta for the tau, right? And these guys, as before with the mirror plane, are 90 degrees apart, right? And then it's tau over 2 below the perpendicular line to sigma tau passing through A. So again, let's just review with the little pencil, with the little pen here. So here's our original rotation of point A. Over here, offsetted by delta, we have our sigma tau, right? Oh, I forgot to put that in here. Whoops. And these guys are separated by delta. Right. So separated by delta, right? Then what you end up with is at 90 degrees, right, away from this guy. So it's got to be this direction somewhere. But where is it going to go as it goes up and down, right? It's perpendicular to this one, but it's below the line that passes through here, which is perpendicular to sigma tau passing through A by tau over 2. Right? So it's tau over 2 below this line. And that defines where the other glide plane is. So now we have two mirror plane offset rotation theorems. One is for a mirror plane. We put offset, and what I should do is modify the top here, and that this one is now with a specific case of G plus offset rotation.